Solving an unsteady state material balance problem will all the time involve solving a differential equations. And for those of you who took differential equations, the course, maybe a couple of semesters ago, or maybe you just had a bad experience with differential equations, I planned this video as just a quick refresher on how to solve the types of differential equations that we'll be solving in this class. If you're in differential equations this semester, or you just happen to be a whiz at differential equations, this should hopefully be a very trivial review for you. So we'll just start off really simple, taking the derivative of a function with respect to any variable. If v is not a function of t, so in other words, I could say that if, in this example, v is volume and t is time, if volume is not a function of time, or if your dependent variable is not a function of your independent variable, what is the value of dv dt? Then dv dt is equal to 0. All right, easy enough. If the dependent variable is not a function of the independent variable, the derivative is 0. What if you are multiplying v by something else? So let's take, this is one that we'll see sometimes. Ca is going to be the concentration of some chemical species A times volume. This is another way to express mass, by the way. We'll talk about all this a little bit later. And we'll say again that if V is not a function of T, so let's say if we have constant volume, but maybe not constant concentration, not a function of T, then the value of dCAV by dt is going to be, the V can get factored out. And that is improper calculus speak, but this is how I like to think about it. I can take this V out of this derivative. What if V is a function of T, or what if volume and concentration are both changing with time? So dCAV times dt, and if both Ca and V are functions of time, this is how I express that mathematically. So Ca of time and V of time means that both concentration and volume are functions of time. Then computing this, I can use, I always learn this as the chain rule, but this is incorrect. It's the product rule. So I could say V times dCA dt plus Ca times dV dt. In other words, I'm taking one variable out and then taking the derivative of the other one. So treating one of the variables as a constant while I take the derivative of the other one, and then switching it. And say at first you thought that V of t was a function of time, but then later on you assume that it's constant. If you later decide that if V of t is constant, then dV dt is going to cancel out anyway, and you're left with the same thing that you had from before, which was when only Ca was a function of time. So these two things are not mutually exclusive. It's just another way to think about it, or a more general way to perform the calculation. Let's say we have a separable differential equation. And separable, remember, means that your independent variable and your dependent variable may be separated onto separate sides of the equation. How do you spell separable? I think it's separable. Separable differential equations. And this means independent variable and dependent variable may be isolated to their own sides. To their own sides. So as an example, let's take dy dx is equal to 3xy. This is a separable differential equation because I can perform simple operations to get the x's on one side and to get the y's on the other side. And that's the first step to solving a separable differential equation. So step one is to separate the variables onto their own sides. So if I'm starting off with dy dx equals 3xy, I would want to multiply, this is again improper calculus speak, but quote, multiply the dx to both sides to get it onto the other side such that are going to be together. And then also divide both sides by y to make the y's together. So my first step is going to be dy over y is equal to 3x times dx. Step 2 is to integrate both sides. So integrating both sides is going to give me dy over y equals integral of 3x dx. And the integral of 1 over y, this is going to be one that you definitely want to memorize if you have not already, is the ln of y. There's a few other integrals that are going to be useful to memorize, but in this semester where everything's online, you'll always have access to integral tables or anything like that. So ln of y is equal to the integral of 3x dx is going to be 3 over 2 x squared. So again, if you're uncomfortable taking integrals like this for polynomials or simple functions like this, definitely you want to review that before moving forward. And I actually have, this is poor form, I forgot something. So remember, if I don't have bounds on my integral, I cannot forget about adding a constant of integration. So the proper way to perform this calculation is to remember the plus c. Now, technically, both sides have a plus c. They're separate c's, they're not the same c, but I can subtract one of them over to the other side and lump it together as a combined constant c. So you only need one of these, you don't need two, although technically there are two, you can combine them. Constant of integration. All right, you cannot forget about that if you have an indefinite integral. Now, if you have bounds of integration, you don't need the plus c, but in that case, you have a separate step where you take care of what that is anyway. Okay, the third step is to solve for your dependent variable. Solve for y is a function of that. I'm going to keep it general. Solve for dependent variable as a function of the independent variable. Okay, so y is my dependent variable, as it typically is. In order to solve for y, I need to multiply both sides of this equation, or take the exponent of the entire thing. Right, so exponent of ln is going to undo that operation. So y is equal to the exponential of this entire side. So I'm going to put an exp there. And when I do that, if I have an exponent of two things added, I can take the constant out front. So e to the c is not the same c, it's going to be a different c, but the fact remains that it's still a constant. So c times exponent of 3/2 x squared. Okay, that is step 3. And then step 4 is solving for the constant of integration with a boundary condition. And that's an important vocabulary word for differential equations. The boundary condition or an initial condition is a type of boundary condition or initial condition. And this is a value of the dependent variable for some independent variable value. So for instance, if I knew that at x is equal to 0, y was equal to 1, that is a boundary condition that I can use to solve for my constant of integration. So let's actually do that. Let's say that at y of 0 is equal to 1, then I would plug in all known information to this equation. So when x is 0, y is equal to 1. 1 is equal to c times exponent of 3/2 0 squared. 0 squared is, of course, 0, and that negates this entire thing. Exponent of 0 is 1. Therefore, the constant of integration is equal to 1, and my final form would then be y is equal to exponent, where the 1 is out front and implied, 3/2 x squared. All right, try these on your own. So I'm going to write these down, and I recommend that you pause the video to see if you can solve them. I will do them one at a time. So dy dt is equal to 2 minus t. And we'll say that our initial condition for this one is that y of 0 is equal to 1 again. And you might have a more complicated initial condition, but you treat it the same. So go ahead and pause, see if you can work this out. And I will do it at the same time, so I may skip a couple of steps. But I'm just going to take the dt over to the other side and integrate. So y is equal to 2 times t minus 1/2 t squared plus c. Plugging in my initial condition gets me 1 is equal to 0 minus 0 plus c, and therefore c is equal to 1. And my final solve form for this differential equation is y of t is equal to 2t minus 1/2 t squared plus 1. All right, simple as that. Let's try another one, slightly harder this time. How about dy dt is equal to 2 minus y? Where again, I'll say the initial condition is y of 0 is equal to 1. Now I have to take the 2 minus y over to the other side and take the dt over to the other side. So the integral of 1 over 2 minus y is going to be a minus because this is the chain rule now. The minus has to come out front. Minus ln of 2 minus y. So that's the inside derivative has to come outside the ln. And then the argument of the ln is the same thing as the function on the bottom. Minus ln of 2 minus y is equal to, on the other side, now I don't have anything, I just have a t. Now I have to solve for y as a function of time, so that is going to make me take the exponent of both sides. So 2 minus y is equal to e to the minus t, and I forgot my c. Keep forgetting that. That's a bad habit to get into. So c e to the minus t, and then solving for y is going to get me 2 minus c e to the minus t. Plugging in my initial condition of y of 0 is 1 gets me 1 is equal to 0. 1 is equal to 2 minus c e to the minus t is 1, right? Because t is 0, e to the 0 is 1. And therefore, c is again equal to 1. A lot of easy examples here, right? So the final form for y of t is 2 minus e to the minus t. Is that final answer? One more quick example. This will be the toughest one yet. We'll put them both together. So dy dt is equal to 2 minus t times 2 minus y. Still separable. Same initial condition. Y of 0 is equal to 1. And we've done these two integrals before, just recently. So I know that the left-hand side is going to be minus ln of 2 minus y. Right-hand side will be 2t minus 1/2 t squared plus c. And now I have to solve for y. So 2 minus y is equal to c e to the 2t minus 1/2 t squared. And then y, solving for y is 2 minus c e to the 2t minus 1/2 t squared. And plugging in my initial condition, 1 is equal to 2 minus c e to the 0. Where again, c is equal to 1. C is not always going to equal 1, by the way. Just warm up calculations to get you back into the swing of solving these. E to the 2t. These should all be exponentials. If I wrote these as actual exponents, you don't need to write exp. Oh, that was, I think I had this question earlier on in the semester. Exp is the same thing as e, but it makes it so that I can write the argument all in one line. I don't have to write it as an actual exponent. I think that can be clearer sometimes I'm writing on a unlined surface like this. All right, so that was a calculus refresher. In the last video for today, I'll get into actually solving an example problem of an unsteady state balance.